Okay, today is going to be our lecture on wave optics, as well as a lab on wave optics. We have an exam 1 week from today.
What?
Yeah. And this is the last material that will be on that exam. Yeah, I know, it's exciting time. So, what is wave optics? Up to this point, we've been doing optics, right? We've been doing geometric optics. We've been treating light as if it has a starting point and no ending point. We call that a ray model. And that model is very well exemplified by using a laser. So here I have a laser. Turn on, please. There it is. So the laser sends a beam back there, and you can see, it's just traveling a straight line. Everybody's pretty much comfortable with that, right? By the way, don't look into the laser. I think that we forgot to take out the one that didn't work very well, didn't we, Andrew?
Yes.
One of them doesn't work very well. Don't look down it to see what's wrong. I actually, when I was in graduate school, a guy that was one of the supervisors in our lab had done that. He had been working with a high-power laser beam, getting no signal, so he looked down to see what was going wrong. The laser beam was hitting the side and scattering, so he wasn't getting a strong beam like this. He was getting a strong beam like this, and it was still enough to damage his eyesight, so he could hardly see with one eye because he looked in.
How quick was that?
That would be a split second. Right? It was a high-power laser. I did my research with the lasers that are used for laser eye surgery, which also would, if I had looked in that, would have damaged it quickly. I came home from work with sunburns all over my arm from light reflecting the 4% or so reflection you got off of a piece of quartz. Yeah. So we wore glasses to protect us. It's very important, that thing. By the way, those green laser pointers like I use for astronomy lab? Some people use those for presentations. Really bad idea. Those little green laser pointers are taking infrared light and using frequency doubling crystals to get it into the green. But a lot of them are not blocking that infrared, and so you get a lot of infrared coming out that could really damage your eyes. So those green laser pointers, I don't like even being in the room with somebody using it because there's, they point here and it splatters all over the room, and I'm worried about my vision there. Just some things to be aware of. It seems like nobody pays attention. So what is wave optics? Wave optics is looking at the wave nature of light. Now, a little history. I think I mentioned earliest optical theory that I've read about was the tentacle theory that said you have tentacles that come out of your eyes.
Feel it.
Yes, you feel everything. Well, by the time we got to Isaac Newton proposed that light behaves like a particle. And he came up with explanations for how all of optics, the things we say, refraction and so on, work with particles. He wasn't exactly right, but he came up with theory now. But then Thomas Young did an experiment that showed absolutely that light is a wave. And so his experiment was to have slits and have light go through both of the slits. And think about what would happen if you... Okay, wait. If you were throwing baseballs and you had a fence with two slats missing. If you're throwing baseballs and it goes through the slats, what do you expect to see for the pattern of the balls behind?
Slat.
A board. So you have two boards missing, so the balls can go through those two missing boards. What kind of pattern do you expect to see for where the balls end up? Yeah, you'd expect to just see them behind those two. So you'd expect to see something, and my whole lecture today has no slides prepared to go with it, which is unfortunate. So let me put in like a whole bunch of slides so I have room to do whatever I want. So if you had something like this and you were throwing balls at the fence, you'd expect to essentially see two piles back here. You'd see a bunch of balls here and a bunch of balls here, and that's it, right? That's a particle description. But what Thomas Young saw, instead of just seeing two spots, well, let's see, analogous, what Thomas Young saw. Let's see, where did I put my... This. So this here is essentially what Thomas Young did, except for it's a whole bunch of slits instead of two. The reason for a whole bunch is it makes it just much clearer. So I'm going to shine this to the back of the classroom, and now I'm going to put it through the slits. Okay, you can't really see much of anything, can you? Let's go to something closer. Without pointing at me, I should mute this while I'm at it. So let's do it like this. When the light goes through the slits, you see multiple dots. And can you see a third one there? Right now it's at the edge over there.
Yeah.
And if I keep moving around, there should be a fourth one, although it's not bright enough for me to see.
I can see the fourth one. Oh, yeah. I got the beginning. 1, 2, 3, 4, 5.
Well, no, from the center. There are two out on each side that I can see here easily.
You know, there was two on the side, and there was one that was just like to the right of.
Anyway, that's more than just two spots, as was expected if it was a particle. And so what Thomas Young said is, well, we've already learned Huygens principle. I have these waves coming out, and those waves, yeah, thank you. Those waves come through here, and following Huygens principle, it acts like point sources. And so you have places where your wave fronts match up, where we have what we call constructive interference. Two waves are in phase and they add to a bigger wave. And then you have in this direction, you have constructive interference. And then you have in this direction, constructive interference. And in this direction, constructive interference. And in between, you have destructive interference. So if it was just two slits, the pattern you get if it's a wave is going to be something that has a bright center. Oh, I want to change color. Okay. A bright center gets dim, brighter, dimmer. Like that. Now, we are not going to, usually I spend a lot of time doing the math on this. We're not going to do the math on this. What Thomas Young calculated is that if you have two slits separated by distance d, so this distance here is d, then d sine theta is equal to m lambda for constructive interference. So I better put a subscript m here because there's different thetas. M is an integer. Any integer, positive or negative. So one thing that you're going to do in lab today is do an experiment to verify the truth of this. So you're going to use a laser like I have here. Now, you probably noticed there's no procedure written in your lab guide. You need to figure out exactly how you want to do it. But you're going to use that laser, and you're going to use a diffraction grating. And my recommendation is using multiple trials. You use the diffraction pattern to determine the wavelength of the laser. Then ask Andrew or me what the wavelength of the laser is. We tell you. And you find a percent error difference between the wavelength of the laser and what you found. If the wavelength, if that percent error difference is small, then you have confirmation that this is correct theory. If it's not a small percent error difference, Well, then not so good. Now, what are these? I gave you these to be in class. You can put them on. What are these things? These are a whole bunch of slits put together. And I'm going to shine the laser through this up at the ceiling so you can see, look at that. That makes a much more interesting pattern. How's that working?
It's being diffracted.
It's being diffracted. Diffraction is the name for this process, but it's being diffracted in more than one direction. What does that suggest? That the slits on this are both horizontal and vertical. That's what you said, right?
Correct. I'll claim that.
I thought I heard you say it. Now, what is this good for? Well, if you're up here and you look at that bright light, you see pretty rainbows. So I didn't bring out, usually I adjust the intensity of the light bulb, but I forgot to bring out the variable transformer. So I'm just going to plug this into wall power. If you look at that light bulb is, of course, producing light. That's what a light bulb is supposed to do. And you should see a whole rainbow of colors coming off. You see rainbows coming off in actually 8 directions because you have vertical gratings, horizontal gratings, and the diagonals is the combination of vertical and horizontal together. But what you can see is we have all of the different wavelengths of light represented here from that incandescent light bulb. It's hot, it's giving off light in the entire range of colors. Now, like I said, usually I heat it up and cool it down. If it's cooler, you don't see the violet and blue. But when it gets hot, you get more violet and blue. That's actually one of the things about our sun. What color does the sun trace? White. The sun is white, which means that the sun is giving us its peak emission is somewhere in the middle of the spectrum. If the sun was yellow, its peak emission would be closer to the red side of the spectrum. And if it was blue, its peak emission would be closer to the blue side of the spectrum. So when you look at stars, like if you can find Orion in the sky, Orion's front foot is Rigel. And you can actually see that it has kind of a blue tint to it. That tells you that it's a really hot star. His back armpit, Betelgeuse, has an orange tint to it. Tells you that all things being equal, that's a cool star.
That's kind of nasty.
What?
Betelgeuse, it's not
No.
cooler than
That's what it is. Now, I'm going to use another type of lamp here, just to keep life interesting. And so here's my other lamp. As with all things in life, you guys probably seen Dr. Clark borrows these every year. You can easily kill yourself with this bad boy. My goal is not to, though. And so I put in there a little tube. And I'm pretty sure this tube has hydrogen gas in it. So let me plug her in.
Yeah, you're right. So the double you added,
And now if you look at it, looks a pinkish color, but if you look through your glasses,
you turn off the projector.
Yeah, don't want to, but I will. You can see specific colors out to the side, not a continuous spectrum. Now you can also see a lot of small colors in there. That's because water is leaking. If this was pure hydrogen gas, you wouldn't have all those little small things. You'd only have the ones that are bright. And so what this is showing us is this lamp is not putting out a continuous spectrum of colors. It's only putting out certain colors. And using this wave property of light, the diffraction grating, spreading the colors out by their wavelength, we can measure very carefully what the different colors are that are present there. And as we'll learn later, we can then determine the energies and whatnot of the photons. So this is all dealing with the wave nature of light. There it is. Oops, I had that on the whole time. Forgot. And so that's one of the things you're going to be doing, studying for the wave nature. Now, this is a very abbreviated coverage of diffraction. So let's just make sure I have the definition of diffraction. Diffraction is the result of light bending around a corner. We tend to think that light travels in straight lines, like I showed with the laser beam. But if I have an edge, the light will bend around the edge. And diffraction is measuring the interference that's produced when the light bends around a corner. The equation for bright or constructive interference is this equation right here, and that's what you're going to confirm in your experiments by determining what wavelength your laser is and then comparing it to what the wavelength of the laser actually should be. I'll actually tell you, these are all helium neon lasers with wavelength is 632 point, I believe it's 8 nanometers. So that's the wavelength that you should be comparing against. No one has asked, because you probably didn't think to, why do these glasses have a whole bunch of lines instead of just two? Remember I said Thomas Young did 2 lines. Why do they have a whole bunch of lines? Okay, she's right. It gives us a clearer picture. I believe in here, these are the optics kits you're using. I believe I have something here that has like just a double slit. I would have to look at it carefully, but depending on the number of slits, you will have a different clarity in your pattern. So let me plug the laser back in. This presumes I can find the laser power. This one. And now the really hard part. Holding this and making it go through a slit. So can you see I got to turn off the classroom lights again. So I'm trying to look down to make sure I'm going through the slit, and I don't know where I'm pointing up there. Yeah. So there it's going through a double slit. Notice you see what looks like a line, but if you look carefully, you have dark spots. Those dark spots are where you have destructive interference. You have destructive interference at just one point if it's 2 slits. That's one point between each bright spot. And so you mostly see the bright spots, and you don't. And the dark spots are the ones that you can pick out. But if you do a diffraction grating, because you're a little bit out of phase with, that's not a grating. Thought it was, but apparently not. When you're a little bit out of phase with the 2 slits, it still looks pretty bright. But with the grating, you have a whole lot of slits, and your phase variation is, phase means when its peak occurs. It's randomly distributed, essentially. Well, it's equally distributed. And so you have, on average, destructive interference everywhere except for where you have constructive. So the diffraction grating with lots of slits is done because then it's destructive everywhere except for where I gave you that equation. So once again, that's what you're working with. Now I'm going to move forward to the next topic. And the next topic is, one of the very coolest things we do in physics. And you know how much cool stuff we do in physics, so it's got to be really cool. Good. So the next one is polarization. So polarization is something that can only occur if you have a transverse wave. So think all the way back to when we first learned about waves. We have longitudinal waves. What is a longitudinal wave?
Does it move? It moves with the direction of the propagation?
Yes, a longitudinal wave is where the displacement is parallel to the velocity. Transverse waves are where the displacement is perpendicular to the velocity. Now, with electromagnetic wave, as predicted by James Clerk Maxwell, what is oscillating? What is
Transverse?
the what?
The transverse.
Well, what is oscillating was the question. Not is it transverse or longitudinal, but what is oscillating?
The electric and magnetic field.
The electric and magnetic fields, hence the term electromagnetic wave. So we have electric field, magnetic fields oscillating. And remember our right-hand rule relationship, that the electric field, the magnetic field, and the velocity are all mutually perpendicular to each other. So if the oscillation is in electric and magnetic fields, and those are both perpendicular to the velocity, what kind of wave do we have? Longitudinal or transverse? I pointed to you because you...
I clicked after I said it.
So what kind do we have? Transverse, because the oscillation is perpendicular to the direction of propagation. Well, in a transverse wave, we'll just focus on the electric field. It has the magnetic field, we're just going to focus on the electric field. Typically speaking, the electric field of the light coming from my forehead to you is going to have electric fields going like this and this, all different directions perpendicular to the direction between me and you. Right? That's just the way the cookie crumbles. If we were going to polarize it, we'd do something to make it so the electric fields are only oscillating in one direction. So how do we make that happen? We take something like the polarizer. This polarizer is actually created by taking a polymer, stretching the polymer, and when you stretch it, it forms a bunch of little cracks. And then they put in electric dipoles, and those electric dipoles line up with the cracks. And then they let it come together. Now those electric dipoles, they will conduct a little bit in the direction of their dipoles. And so if I have electric field coming like this, it can absorb the energy of the electric fields and make electrons move. And so it'll absorb light. But if the electric fields are going like this, you can't have anything move this direction because the electric dipoles are this way, and so it goes right through. And so this blocks light that has oscillations in one direction, allows light with oscillations in another direction. So, and for this, there's a way to use the camera on that thing, but just come on up. It's more fun to see it in person anyway. We have lots of cool things to see. First, I have to get this. I just turned it off and on because I forgot I had to change the lamp. That was what was missing. Okay, so here's my light source. I put this polarizer on. How would you say the intensity here is compared to here?
It's less.
It's less, okay? Now that was pretty simple. According to theory, you're going to have, on average, your light is the same amounts in all direction. And the electric field is being attenuated so that only the amount of the electric field that's parallel, let's say that this is allowing light through this way. Just I'm using this little track here as my guide. So if it's allowing electric fields this way through, then if you have an electric field like this, you break it into components. And you have part of it that's parallel and part of it that's perpendicular. Cosine theta times the total electric field is the amount that's parallel. And so if you take the electric field and you square it, that tells you the intensity. And so you take that electric field squared, and you have cosine squared theta times the original intensity is how much intensity gets through. So you have intensity that's 100% this direction, like 50% this direction, 0 this direction. Now, if I put another one on top and I line this one with it, what difference should I have? If this is allowing only electric fields this direction through, and I put one that's again going to only allow this direction through, what's it going to do?
Same thing.
So will it be brighter, dimmer, or the same?
Same.
Okay. Now, if I put it on here, you see it's a little bit darker. Why?
Oh, because there's some coming out like this, and then those are broken up again.
Good thought, but it's actually more mundane. These aren't perfect. That's why. If they were perfect, you wouldn't be able to tell the difference. Now, what's going to happen if I rotate this?
Ooh.
Doesn't get darker very quickly, but there you see it's getting much darker, right?
Yeah. It was kind of darker at an angle. I'm looking down. Like, okay.
It was actually.
From where I was
darker.
standing, so.
This is darker than that.
No.
No.
Really?
No? Maybe it's just how I was looking at it.
Oh no, that
Because that looks darker than this.
No.
No.
No, I see it. I see it.
behind me. Ryan knows what I'm talking about.
Yeah, no.
Okay.
Hey, basketball.
Okay, so now I'm going to put another polarizer between the two. And I have it aligned the same as the bottom one. What difference does it make with the third one? No difference. What's going to happen if I rotate this? Why?
Oh,
Wait,
because
we're
it's
gonna
going to cancel out
rotate.
the top one.
Rotate it all?
I'm going to rotate this.
Oh,
So this one is still going to remain perpendicular to that one.
that one should get darker. No, it should get lighter.
Yeah. Whoa.
And if I keep going, it gets darker again. So at 45 degrees, I get the most out. Why do I get, okay, the bottom one's only allowing light like this through. The top one's only allowing light like this through. How do I get light through when I have all three stacked?
Because the
Because
components
there's a
of the other
component that's
two.
being preserved.
Yeah.
Yes, this one here is going to take the okay, so the bottom one is allowing light like this, but light like this has a component in this direction, a component like that. And so this component is allowed through, but now this is like this, that has a component in this direction. And so you're actually changing the light by having the one in the middle. So, more fun things. Oh, I got tons of fun things here. This here, okay, that's tape. Did you bring my tape back?
I left it in the room.
Okay. Nothing special going on here, right? Put this underneath. Put another one on top.
What?
Wow.
Go ahead and rotate it.
Science.
Let's rotate it. Wow.
Oh, it goes away.
Stained glass.
Kaleidos.
That's how they make
How does that work?
Science.
Anybody taking organic chemistry?
Yes.
Anybody studied things like
Optics?
the optics in your organic chemicals? You measure, you know, if you have a racemic mixture,
Oh,
Yeah.
doing
by looking at polarization, right?
Yeah, like if it has a Carl center, and you can tell if it's
Left.
right 'cause it rotates.
So-
polarization to the left and to the left.
Because it'll rotate like.
So, yeah,
We're just paying attention.
with chirality, some things will cause a
Oh,
left
yeah.
rotation.
Yeah.
We're done. Okay, nope, done.
Okay, so that's what we have here. The cellophane tape is causing a rotation of the polarization. That's what you measure there in organic, is the rotation of the polarization. And different colors have different speeds. And so the amount to be rotated is different depending on the color. And so depending on the thickness of the film, you're going to have different colors rotated by different amounts. So you're blocking by color now. You're blocking the ones that were, you know, like this, I'm blocking the ones that will rotate 9 degrees. Like this, I'm blocking the ones that were, no, excuse me. Yeah. Here, I'm blocking the ones that rotate 9 degrees. Here, I'm blocking the ones that were rotated by 180 degrees or 0.
So which one's considered negative?
I don't know. I'm not a chemist.
So I have a question. What's in that?
Cellophane tape.
Oh, that's it? Okay.
So somebody got excited. This is not me. You know I don't have time for this. Union College used to be known for its clock tower.
It's not anymore.
The clock tower was torn down, what, 30 years ago?
Oh, we're not talking about
At
the
We're
class
too
gift.
young to understand what you're saying.
There used to be a clock tower that looked like that.
On the top of a building?
Yes, it was the top of the administrative building.
Did it have a bell?
I think so. Yes.
I
Yes.
don't know, there's just
There's
an old
a bell. Yeah.
And like it
Okay.
says don't hit it, but I really want to.
Do not, BJ. You will
Okay.
die.
So somebody made this, and of course those colors don't look right. So how do I fix the colors?
You turn it.
Rotate it.
And there we have a pretty black sky and a white moon.
Oh!
And of course, me, because I am very patriotic, both to my home country of Liberia and to my country of birth, the United States of America. Both of them have very similar flags. So, right, there's the U.S. flag.
And make it.
Kinda. There, perfect. Except for what's imperfect about that? Well, it has, I think it
It
has
has
stripes.
the-
1, 2, 3, 4, 5, 6, 7.
It has like weird lines on the
It has the right stripes. Has red on top and bottom.
Oh, see, this angle just throws everything off.
So does
I
this
see a
one.
blue flag from here.
Yeah, the other
Yeah.
one.
Oh, really?
Yeah.
Yeah.
So that's-
it's a
Yeah, I was gonna say, well, I'm saying it's
Yeah,
blue.
that's also why I thought it was dark at the angle. Everything's thrown off from how I see
Notice
it.
the stars.
Mm.
1, 2, 3, 4, 5, 6 by 1, 2, 3, 4, 5, 6, 7, 8. 6 times 8 is 48. This had to be made
Before Alaska.
before Alaska and Hawaii.
So,
Hawaii was 60 years ago this week, so Alaska was only like a little bit before that.
yeah.
So this is more than 60 years old, right?
Or
Either
they
that or the
just
person was
didn't do
really
it
lazy. Yeah.
They just don't believe
I mean, when you do this much work, wouldn't you do it right? Think about how
Alaska's
much work that
Hawaii.
took. Okay.
You almost said countries.
Nuh-uh, no,
Yeah,
I
you
don't
did.
do that.
Who cares about those?
Literally, the only thing you're missing was a Y.
Hawaii was its own nation, so I'll give them
All right.
that.
So here is Calcite Crystal. These are both Calcite Crystal. I don't know which one's better. I think this one's better. I stole this from Richard Clark a few years back. Okay, so check that out. What do you see through it? Actually, maybe it is better with
Double
this one.
R.
Double R. Because
Yeah.
R is supposed to stand for Richard, double R stands for Rolls Royce. Right? Now, go ahead and rotate the crystal. He says whoa before he starts even rotating. What's happening?
Oh.
It's like it's moving. The R's kind of like
Yeah.
Okay,
circling
you have to be
around
at
the
the-
other R.
Part is moving and part is not.
Oh, okay.
Part moves and part doesn't.
No, I didn't.
You see. Oh, I see. So what would make it move? Think about the physics we've learned about optics. What would make it move? Light is being
Bend.
bent. We call that refraction. Refraction. When it goes from one material into another.
Mm-hmm.
We have one part that's being bent consistently no matter how much I rotate. The other part is changing.
What do you mean by changing? Sorry to be
Changing is changing how much it bends, right? It's bend like this direction. If I move it around now, it bends this direction,
Okay.
bends that direction. And so we have what we call the ordinary and extraordinary axes. We have one axis with the one speed of light, another axis with a different speed of light. And as we rotate it, the directions with the different speeds are changing, and so the directions of the refraction is changing. Now,
No.
polarizer. What's going to happen when I put the polarizer on there?
When you get darker.
You're gonna not see one R.
You don't see one R. Now, if I rotate it,
Wow.
I can make it so the other one appears or disappears. So I can change it from one to the
It's
other.
like those neon sites in cities.
No, but right. So I can
Or
make it so one
realization.
appears and the other appears. So clearly, there is a polarization effect. Light that's polarized one direction has one speed. Light that's polarized perpendicular to that has a different speed. Cool stuff, right? Okay, last thing. Way too many 3D movies by me. Y'all ever gone to 3D movie?
Yeah.
Oh, it won.
One.
No one.
Say, that's the real piece.
Okay, let's not use
Yeah, he
this
goes
one
with
mirror.
buckets.
Grab that mirror.
Oh, I'm sorry.
Now, one brave soul has put on glasses with me. Ryan, look at yourself in the mirror. What do you see?
Ugly.
Oh, ooh.
Yeah, I got a little bit.
I mean, besides handsome and all, what do you see?
You can't really see through the.
Look at your eyes.
Yeah, you can't really see through the lenses. A little bit. I don't know why. What am I supposed to see?
Here, look at your eyes.
I mean, a second.
What do you see when you look at your eyes?
Thank you.
They look kind of fake.
For anybody.
They look kind
Yeah.
of fake.
Fake eye?
What's
No, but like.
fake eyes? Okay.
Okay. To make it more fun, look at somebody else's eyes.
Play my eyes.
Yeah, see, like,
Oh,
I
yeah.
can't really see that well.
Close
Oh,
your
really?
close your left eye and look at somebody else.
Oh,
Close your right eye and look at them.
That is kind of cool.
really crazy. Can I show you?
Close your eyes. Close your eyes.
Kind of
Oh, wait, what?
Yeah.
What in the world is happening here?
Polarization.
I noticed this when I was in a movie. I looked in the mirror while I was
Oh, one is
washing my hands, and I was
polarized
like,
this, and
my
one's
eyes are going like
polarized
this.
Yeah.
Because
That's
I'm
why.
constantly shifting back and forth between which eye I'm looking with. And when I look with this eye, I can see,
So one's like this and one's like that.
almost.
It's,
Rotate. Okay, so close one eye. Now rotate your head. Keep looking at me. What happened?
It switches to the other one.
No.
No, it doesn't. No, it doesn't. If you go and watch a 3D movie at the Henry Dorley Zoo, right, in their IMAX, they give you these glasses that are big old things, right?
Mm.
And those glasses are smaller versions of this. One's oriented one way, one's oriented the other. So if you turn your head, everything is going to shift. These are a more advanced technology.
That's not.
These are more advanced technology. They use what we call circularly polarized light.
What?
The light. Okay, so yes, explain. How do you have circularly polarized light? Well, you have electromagnetic wave, right, oscillating like this. Well, what you do is you introduce a second wave that's oscillating like this. So you have one like this and one like this. And you have them in phase, so when one's like that, the other one's like this. So it goes. And so this one's at 0 horizontally, and this one's at max. This one's at 0 vertically, and that one's at max horizontally. If you look at the electric field vector, summing those up, the electric field vector just spirals like this. It stays constant magnitude, spirals through space. And so we call that circularly polarized light. How they do it is they put in, quarter wave plate. So they put a polarizer, so the light goes through and it's polarized. And then they put in what's called a quarter wave plate that will make half of the light delayed by 1/4 of a wavelength. And so then you have that circularly polarized light. And so one of these is right circular, one of them is left circular. That means one of them, the light's going like this, the other one is going like that. And then you go through the reverse process, which is why you close one eye and you see only the same eye in other people for your receiving. So what they're broadcasting when you watch these 3D movies, they have two projectors, one that's broadcasting a left circular and one that's broadcasting a right circular. And then you have your left eye sees one of those pictures, your right eye sees the other picture. So your eyes are seeing two separate pictures, your brain puts it together to give you the 3D effect. Whereas at the Henry Dorley Zoo, they're using a vertical polarizer and a horizontal polarizer. And as long as you keep your head vertical, one eye sees the vertical and one eye sees the horizontal, works great. But if you tilt your head, then you're getting some of both with each eye and it breaks it. These here, you can tilt your head, it doesn't break it. Now I have to point out there's one more thing. You don't break it when you tilt your head, but yet you kind of do. Because how do you determine depth? How do you determine how far away something is from you? This is why I stopped playing City League baseball. I started not being able to determine depth. Yeah, you triangulate. Your eyes go like this, and your brain says, oh, at this angle, it's that far away. At this angle, it's that far away. And so those pictures, everything is based on horizontal triangulation. So if you turn your head like this, then they're going like that, and it's not quite matching up. And so the 3D movie technology doesn't quite work when you tilt your head because you're still trying to use cues like this when your eyes are like that. But it's still better than what they have at Henry Dorley with just cross polarizers. So this is what we call polarization. We have the law of you can go back now. I played out all of my cool tricks.
Wow.
And knocked over my here. So for polarization, like I said, and actually this is in the lab guide here, the amount of the electric field that's transmitted is the incident amount times cosine of the angle between the first polarizer and the second polarizer. And the intensity is proportional to the electric field squared. And so if you square that, clearly cosine theta squared is cosine squared theta. And so the transmit intensity is I incident times cosine squared theta. And this is called the law of malice. And notice malice is a dude. It has nothing to do with, an emotion or anything. So in your optics kits, so let's turn to the experiment today. In your optics kits, you have a number of things you're going to utilize. First, you have these little sliders that go on an optical rail. You want to have that? So here's an optical rail. The sliders are magnetic, so they'll stay on there. Push them up against the side that has a ridge so you get everything squared up. You have then two polarizers. So, by the way, one of these is different. The one that has these things hanging off, you're not using that one. So you have the two polarizers. Put one polarizer in, orient it so the little divot on the top is pointing to 0.
Wait, what?
See the little divot on the top? So 0 is pointing back. Put it on here. Then the next one, you're going to want to change the angles to see how much light is transmitted for different angles between the two. So if that one's set at 0, whatever I set this one at is going to be the angle between the two. Put them both on here, of course. We need a light source, right? Here's the light source. It's also magnetic. Put it on there, slide it up. We need to detect the light. I can't use my brain to say how much light got through. So that's why we have the things on this table. You need two things on this table. Number one is, Number one is this USB link. These belong to biology. Thank them for that. Number two is this light level meter. They just snap into each other. This USB link will just plug into a computer. Oh, yeah. Plug it into computer, start up Capstone. It will recognize that you have one of these. And there's actually a preset that has a table of data and a graph. That works perfectly for us. So just select that preset. This has different light settings. When we were doing it in practice, we determined that it would work well with the middle one or the small one if we restricted the light. How do I restrict the light? Let's just put this on. Put that on so we have a smaller beam, so it's not as bright. You do need this so it's in the line of the light. To get in the line of the light, just take this little table, set it on there, make sure that it doesn't move during your experiment. During your experiment, that's going to affect your data, so you want to have so it's somewhat stable there. And good to go. So measure the intensity that gets transmitted for different angles and compare it to the law of malice. Now, I'll tell you right off the bat, it's not going to be perfect. You're not going to get 0 intensity when those are crossed. I swear somebody last year figured out how they could make that happen. I forgot how they did. So that's how you're going to test the law of malice. For testing the diffraction, you'll need to use a laser. So we have the laser that's up front, that laser there, this laser here, and one of these two works. You'll figure it out which one doesn't work. Remember, don't look down the beam saying, is this the one that doesn't work? Because it does, just the beam is not lined up right. And for that, you are going to use the diffraction grating right here. The diffraction grating says 600 lines per millimeter. in the equation that I had up there, and let me just go to where it is in the lab guide. Maybe. Come on, lab guide. There it is. It says sine theta n equals n lambda over d. I have the d on the other side of the equation. It's the same thing. D is the spacing between the lines. If there are 600 lines per millimeter, what's the spacing between the lines? Yeah, 1 millimeter divided by 600. So you know what the D is. It's 1 millimeter divided by 600. Or, if you really are lazy, you can just say 1 over D is equal to 600 lines per millimeter. So you're going to use this. Use a laser. I recommend strongly that you point the laser away from the classroom. I like to use the edge of the desk as a guide so I can make sure that my laser is pointing perpendicular to the wall. Put my grating, I use the optical track to hold the grating again. Measure the distance from the, oh, you do need to make a slit for this. Actually, no, it's a laser beam. Don't need a slit. If it was a light source like that, you need a slit. So, measure the distance from the lens to the wall. Measure the distance from the center dot to the ones on either side. Use that equation to calculate what the wavelength is. And find your average from your multiple trials. Compare that to theoretical. And that's what you need to do for today's lab. Now, you'll notice that there is no procedure written in the lab guide. You're supposed to figure out the things I just told you to do. Make sure you write down your procedure of how you're going to go about doing these two tests. For the scientific method, you don't have to have an observation. Your hypotheses are twofold. Number one, I hypothesize that Malus was right, that blah, blah, blah. Number two, I hypothesize that diffraction follows this equation. And then you have your test. Your test is your procedure. Your results are going to be the wavelength that you found from testing diffraction and how well you fit the law of Malus.
Is that what you want for for our results? Wait,
Yes.
what specific number? You just wanted the wavelength?
That's usually what I just said. The wavelength is the only number. The other one is how well you fit the law of Malus.
So like a percent error.
There.
Do we need to give reasoning for our hypothesis?
No, your hypothesis is just going to be those two.
Can you repeat the second one?
Of the results?
Of the hypothesis, sorry.
Okay, so I'm not sure what order I gave because there's no special order.
Oh, you
So,
gave them the notes.
One is the law of Malus is correct, and the other is that this equation for diffraction is correct. Both of these things are things that can only be happening if light is a wave. I emphasize that now because later on we'll learn about light being a particle. We'll learn more physics, and we'll contradict what we did in class in lab today. So I want you to be able to understand what we did in lab today, so when we contradict it, you understand. Any questions? All right, break up into your own groups, and should be groups of 2. Well, we need to have a hypothesis that says 2 alpha, that is the law of Malus, the light will transmit
Yeah, can't wait.
So actually, because I got class. Sorry.
Yes. Okay, you don't have to have a separate test and procedure as long as you explain it carefully.
And then the hypothesis is. That's fine. Or do you want me to explain?
I would at least put down the equation.
whatever we want to test.
Then after the
I know
second
you're gonna
one.
have to put it, because we're using the.
I put the
Wayne
one
house with the
Oh.
password.
And then in your equation section, you would have to do that.
Yeah.
Yeah, because they're gonna go quick.
Okay. I'm trying to collect all of my little party glasses.
Is there a name for the second one?
So this equation here, that was Huygens?
Huh?
The second one, that was Huygens?
As far as I know, there is no name for it.
So that second part, it's not Huygens principle?
No, Huygens principle is that when light goes through.
Yeah, yeah, it's like a point,
Yeah. And so Huygens principle was used to derive the label.
So, but is it this equation or the one down here? Okay.
This one here is just for geometry. Geometry.
And then the polarization one, how would I like, who did this one?
The log analysis polarization.
Okay. So then that, I just put my hypothesis whether I can get a work or not, or?
What your hypothesis is, I believe that the law of malice, I is equal to I max cosine squared theta.
Is discussion.
That's
So,
that's it.
that's it? For that?
What is the middle of default discussion? Data.
Okay, do I have all of the glasses?
Good talk, good talk.
You know what? I totally get it with last time. Like, I
I know,
have
I know.
and all this makes sense.
That's what I said.
I have to tell you,
Oh, wait.
polarization demonstrations are my derivatives.
It is fun. I
So
my
what
expectation was that.
Yeah, I think those- Oh, it is.
There you go. One has to be a 0 and the other one we get to choose between the
Okay, so
Oh, we
which one are we doing first?
Yeah, we're just gonna shine a light through it and then we're gonna.
Do the
use
laser
that
one
little
first.
USB thingy, whatever to measure the.
There's enough of the other for everyone. There's not enough laser, so do the laser one first. Do that, and then we'll have to
So,
work
you know,
everybody.
once
So Dr. Rad.
Yeah.
For this one, when we're doing the, that's for the second one, right?
This is the
Yeah.
law of malice.
this
Oh,
is
that
the
one,
one.
yeah, that one. So this right here, these numbers here, these are the
I feel like these are okay or no, just like,
what are we measuring? The light?
Oh, no, I think he was talking chirality.
Which.
The word is optically active. Are you sure?
Every 60 days.
But like our hypothesis,
You basically, I just remember it pretty well. It's
But it's, you know, 0 to 90 and it's reflected back in 90 to 100. So if you did it 0 to 100.
I'd say change what change that.
So, wait,
I mean,
what?
I would recommend it.
what one do you want? What do you want?
Oh, okay, so every 10 degrees.
From 0 to 90.
0 to 90 or 0 to 100. So like, I did 0 to 180.
We're doing that.
It does
The raises, I think the raises. This is not going to be.
Yeah.
For, we have to do the hypothesis, right after.
Good, moving on.
Oh, you right? You do. You also need the.
So we just say we're gonna, what is this, a light source or beam? And that's a beam, what is this? It's a light.
It shouldn't be. So you're doing
Light
this
source.
first.
But what if
Using
So we're gonna be shining the light source through two
Like be something to rest it like this.
polarized slits.
Magnus messes my fingers. I'm like a finger count.
Well, this here, this here is used for laser.
His.
It would make it kind of. Oh, that's the track.
Actually, it doesn't make it. You're looking at this.
It's gonna be.
Finger between those.
Okay.
This will be
Is our thing kind of faulty? I just totally see two dots. Not here, not here. On the actual.
Hey Andrew, how specific do you want
Yeah,
to
I
be
didn't
with
see
test?
that.
I'm just going to explain.
Now I can angle it so it's on the black. It's blocked.
You know what's really funny about it? It's coming back again.
Okay, so for the test, so are we just gonna say we're gonna be shining lights through two different
No,
slits?
it's
One will
still-
be at 0 degrees, and the other one we're gonna be increasing by 10
So if it
degrees.
goes off my laptop, does that
through
make
like, what,
sense?
180?
Yeah.
And from there, we're gonna figure out. This.
Sure enough.
No, I
Yeah.
I don't think it is.
Yeah.
See, it's still the same.
The goal is just
My own.
was equal versus.
Okay, so then, so far what I explained about that, then I would say at the end, it was calculate the percentage of error, see.
Okay, we should set it up.
Yeah.
Next, do you want to plug this?
I know what you're gonna add. You're holding it, so you're holding it.
See that?
I'm really not close to it. Now I
Oh.
Honestly.
Yeah. That'll bring the temperature down.
25
Guys, when you get these
DJ, you know how to play them?
can't see it, okay? I can only palpate so much.